Greetings and welcome back to a class in quantitative methods. In the previous class, we discussed the sampling distribution of X bar. There, we assumed that sigma, the standard deviation of the underlying random variable X, was known. What happens if this sigma is unknown? And that is usually the case. In most cases, sigma will be unknown. And that is where we come to this distribution, the T distribution. This may not cause a problem if the sample size is large. And that is because I can use the sample standard deviation S to approximate sigma. But what happens if the sample size is small? And all this started off with Gossett. He was the quality inspector for Guinness breweries. He had to certify the quality of the beer. And in this case, it was difficult to find large samples. For example, it's not very healthy to taste so many beers. And therefore, he came up with this T distribution, which is applicable when you have a small sample size and sigma is unknown. To recap, we know that if n is large enough, for our class n greater than or equal to 30, X bar is normally distributed with mean mu and standard deviation sigma by root n. And this no matter what X is. No matter what the distribution of X is, X bar will be normally distributed provided n is large enough. We also know that if X itself is normally distributed, then X bar is also normally distributed. Now, in the case when sigma is unknown, and especially when the sample size is small, that is n is less than 30, if we have another condition, which is X is normal, then what Gossett found is that X bar minus mu divided by S by root n is a T distribution with n minus 1 degrees of freedom. Notice that in the central limit theorem, we have sigma by root n. Out here, what we have is S by root n. Right? Because in this case, I can write this as X bar minus mu over sigma by root n, which is normal with 0, 1. Similarly, by replacing sigma by S, we get this T distribution, provided the base population X is normally distributed. One more thing, in the normal distribution, I have two parameters, mu and sigma. The two parameters. For the T distribution, we only have one parameter, which is the sample size minus 1. So for each sample size, 2, 3, 4, 5, all the way to infinity, n minus 1 is the parameter for the T distribution. Here's an example of a T distribution where I'm comparing the T distribution with a normal distribution, the standard normal distribution. This black line is the standard normal distribution, and this red curve, is the T distribution with degrees of freedom 3. Which means for our case, we're looking at samples of size 4, and therefore 4 minus 1 is 3, therefore I have degree of freedom 3. Notice a couple of things. One is that it is symmetric about 0, just like a normal distribution. That's one. Secondly, notice that the tail out here is fatter than the tail of a normal distribution. And that is because, remember, when I defined the T distribution, it was X bar minus mu over S by root n. So obviously, there will be cases where the observation of the sample are close to each other, meaning that there will be cases where S is almost 0. which means that there will be cases where this takes on very large values. And that's why the tail is fatter for a t distribution as compared to a normal distribution. In this slide, I have several t distributions and I'm comparing it with the normal distribution. The normal distribution is this black dashed line, the standard normal distribution, and all the others are t distributions. The red line is with degree of freedom 1, the blue is with 3, the green out here is degrees of freedom 8, and the yellow is of 13. So notice one thing, as the degrees of freedom increases, meaning that as a sample size increases, the t distribution approaches the normal distribution. It approaches the normal distribution, and that is the case whenever, if you look at the t distribution tables, you will see that as the degrees of freedom increases, the values in the t table is equal to the standard normal table. In this slide, we have presented an excerpt from the t tables. The t tables is given out here. Notice that the first column is labeled DOF, degrees of freedom, and I've given the degrees of freedom from 1 all the way to 8. And you should realize that this can go further. That is 9, 10, 11, 12, all the way to 100, 200, and so on. The remaining items in the first row are labels. They also designate the area in the upper tail of the t tables. For example, if I look at, let's take these two cells. Number 3, the number 3 refers to a t distribution with degrees of freedom 3. This number 0.9785 is the t value for which the area in the upper tail is 0.2. Meaning that if this were degree of freedom 3 and if this area is 0.2, then this point out here is 0.9785. And that is the way to read a t tables. And like in the normal tables and in any other probability distribution table, one should first look at the top of the table to understand what these numbers imply. So in the top of the table, I have this picture of the t distribution, and it is showing me a shaded right tail. I go down further and I see that it says that the area in the upper tail. So I realize that whatever these numbers are in this t tables, they refer to the area in the upper tail. Now let's try a couple of problems. Suppose the degrees of freedom is 6. What does that mean? When I look at the t tables, I must refer to the row which is labeled 6, and that is out here. This is row 6, which refers to a t distribution with degrees of freedom 6. Now I want to compute probability of t greater than 1.4398. So let me go down this t table, this 0.9, and here I can get 1.4398. And what this table means is that if this is 1.4398, then this area out here is equal to 0.1 or 10%. Therefore, I know that this is equal to 10% or 0.1. Similarly, now let's look at the second one. Now notice here, I've got the same number 1.4398, except that I'm looking at probability of t less than minus 1.4398. And note that t distribution is symmetric just like the normal distribution. Therefore, if this area out here for 1.4398 is 0.1, then symmetrically, if I take the point minus 1.4398, then the area of this tail is also 0.1. And therefore, I can write this as 0.1. Let's take the third problem. Here it's a little different. I want to find T star for which probability of T greater than T star is equal to 5%. Meaning that I want to find the T value for which the right tail is 5%. That's straightforward now. I go to the top of the row of this table. This is 0.2, 0.1, and here it is 0.05. And therefore this column gives me T values for which the right tail is 5%. I go down, because note that my degrees of freedom is 6. So I go down to 6 and I get 1.9432. And therefore this T star for this problem, for the third problem, T star is 1.9432. Let's look at the fourth problem. The fourth problem is find T star for which probability of T less than T star is 5%, which means that we're looking at the left tail. And obviously, if the right tail, if T star is 1.9432, then for the fourth problem, T star would be minus 1.9432. That's because the T distribution is symmetric. Finally, last one, it is slightly tricky, but we are going to use this concept in later modules. I want to estimate probability of T greater than 1.5. Remember, keeping degrees of freedom as 6. So I go back to 6 and now I look at this. I've got 1.4398 out here. I've got 1.9432 out here. The point is that I do not have 1.5. 1.5 does not exist in this table. And you should realize why. The point is that I cannot have a T table for every degree of freedom, which means that I would have had to have had at least a 1000-page notebook. And therefore, what we have done out here in this T tables, it gives you a limited view of the T distribution. So it's giving me that for, look, the area of the right tail, right of 1.4398 is 10%. Area to the right of 1.94 is 5%. Now what I need to know is what is the area greater than the area to the right of 1.5. Okay, let's draw the picture. I got the picture out here, right? This is 0 and I got 1.4 here. I've got 1.9 here and I need to have 1.5 here, right? So now the point is that probability of T greater than 1.5, that means the area to the right of 1.5 will be greater than the area to the right of 1.9. So I can write this as probability of T greater than 1.9. But it will be less than the area to the right of 1.4. Area to the right of 1.4. Therefore, this is probability of T greater than 1.4. And that's exactly what I mean by estimating the T value. And this idea we are going to use in later modules. So please just remember that. In this session, we have discussed the rationale for the T distribution, the convergence of the T distribution to standard normal, and finally, how to read the T tables. Thank you.